Hi, my name is Abdelatif,
And I'm Ryan Bronson.
and this is our final project on characterizing photodetectors.
The focus of this project is to characterize two different photodetectors as a function of their spectral response.
The two detectors analyzed are the silicon photodiode and the cadmium sulfide photoresistor.
Detectors produce an electrical signal proportional to the amount of light incident upon it. So how does a silicon photodiode produce a current?
A silicon photodiode consists of a p-type and an n-type material. When two electrodes are connected to the p-n junction, a depletion region is formed, allowing electrons to flow from the n-type material to the p-type material. This induced electric field within the structure increases with incident light, effectively increasing the current produced.
In a photoconductor, light absorbed by a semiconductor material separated by an insulator allows the number of free electrons and holes to increase. This causes the electrical conductivity of the material to raise. As the illumination increases, the resistance will decrease. This physical response can be demonstrated by building a function-generating circuit. As incident light increases, the pitch increases.
A photon incident on a semiconductor has the ability to excite an electron within the material structure. If photons possess sufficient energy, greater than or equal to the material's band gap, electrons will leave the valence band and jump into the conductive band, leaving behind a hole. The responsivity of the detector's material should then peak for a corresponding wavelength of sufficient energy. The maximum wavelength is inversely proportional to the band gap of the material. We then expect a peak response of 1000 nanometers for silicon and 512 nanometers for the cadmium sulfide detector.
In order to experimentally prove this, we need a monochromatic source. A monochromator can be used to achieve light of a single wavelength. This device consists of a collimator, diffraction grating, and a movable aperture stop. Let's see if Google can help find a monochromator for us. Maybe the remote sensing group will let us use theirs.
The remote sensing group in the College of Optical Sciences is best known for its work on in-flight radiometric calibration of remote sensing imagers.
The remote sensing group's monochromator is controlled by a computer in which a custom program can change the output wavelength.
A half millimeter exit slit is inserted into the monochromator. We can expect a half bandwidth of approximately 1 nanometer.
A halogen source is used. Now it's time for us to test our silicon photodiode and our photoconductor. We will connect the photoconductor to a home-built stand, connect leads, and connect it to a DMM to measure the resistance.
The photoconductor is then placed directly in front of the monochromator's aperture.
The silicon detector is then connected to the monochromator and computer for automated data recording.
The responsivity of the detector in amps per watt is being plotted over the visible and low-end infrared spectrum. Max response for the silicon and cadmium sulfide detectors are expected around 1000 and 500 nanometers respectively. Using the manufacturer's spec sheet for comparison, a shift in peak wavelength of about 10 nanometers was observed, most likely due to quantum efficiency factor, or the conversion efficiency of an incident photon to a charge carrier. Semiconductor technology allows devices like photoconductors to respond to light levels similar to that of the human eye. In conclusion, the material used to manufacture the detector inadvertently affects the peak spectral response wavelength.